Okay, so this is Debarati, commonly called Debbie. Thank you very much to the organizers, particularly Sarmistha, Manjari, and Prashanth, for organizing this wonderful conference. Even if it's virtual, it's got the entire community back online. I'm enjoying this whole session very much, and particularly I've been transitioning in the past year. Like Sarmishta said, I moved from Europe to India, and a couple of weeks just before lockdown, I joined as a professor and faculty at IUCAA in India. And this meeting gives me a chance to present a recent study that I've performed over the past couple of months with an undergraduate project student, and a follow-up of this work, which is being performed by a graduate student of mine. So earlier today, we already heard very nice lectures, pedagogical lectures from Deepankar and Jocelyn. This makes my life easier because I think you already know the motivation of my talk, but so let me explain. So the motivation is this, that neutron stars are observable throughout the electromagnetic spectrum. So we have, thanks to the advancement of technologies, we have at our disposal, we are able to observe these objects at multiple wavelengths. And from these, we are able to derive a number of astrophysical observables, like the spin period, the mass, the radius. Already Jim earlier during this meeting talked about in great detail the different observables like mass and radius and how they are determined. Moment of inertia, compactness, temperature, magnetic field, and so on. So this gives us a fairly good idea about the global properties of neutron stars. But what is a big challenge is to be able to describe the interior of the neutron star. And the reason is this, that from the mass and radius, we have an idea of how dense the matter inside the core can be. And back of the envelope calculation tells you that the densities in the core of a neutron star can shoot up from 2 to 10 times that of saturation nuclear density, which means this is far more extreme compared to any terrestrial experiment that we can ever imagine here on Earth. So going from the surface to the interior, we encounter different types of matter, and like only the surface nuclei are close to what we can observe in terrestrial experiments. As we go towards the interior, the densities increase rapidly, the energies of the constituent particles start to increase, and then we go from nuclei with background electrons to free neutrons. So neutrons start to drip out of the nuclei. And so this is the inner crust. And beyond the inner crust, the densities are so high that even these nuclei start to get deformed. And finally, they melt into a homogeneous liquid in the outer core, comprising of free neutrons, protons, and electrons. The protons and electrons because of charge neutrality and chemical equilibrium. And even more mysterious is the inner core, because what happens at densities which are far above 3 times saturation density is not clear to us even now. So it is predicted that there could be strangeness containing matter like hyperons, condensates of mesons like antichaons, and even deconfined quark matter that could appear in the neutron star interior. And so it's a big challenge to be able to understand how such particles appearing in the neutron star core could affect global properties that we observe with our telescopes. So one entity which has been described throughout this meeting is the equation of state, and which is basically the pressure density relationship. And already Jim earlier talked about how the pressure density relationship can be translated to observable quantities like the mass and radius. So basically we have to solve the Tolman-Oppenheimer-Volkoff equations of hydrostatic equilibrium consistently with the pressure density relationship in order to obtain the mass and radius. So this figure was also shown. So we have an idea about the masses, particularly for double neutron stars in binaries. And so earlier it was thought that most of the canonical neutron stars have masses clustered around a value of 1.4 solar mass. But then in 2010 came very special observations about very massive neutron stars, the 2 solar mass neutron stars. And this produced a new puzzle called the HYPERON puzzle. The reason is this. So if I go back to my previous slide, so you know that nucleons, so appearance of new degrees of freedom in the form of hyperons, for example, this would lead to a softening of the equation of state, a lowering of the pressure because of new degrees of freedom, and correspondingly a lower maximum mass. So the question was whether hyperons can still exist in the neutron stars with such high masses. And so I was working at the time in the group of Jürgen Schaffner-Bielisch in Heidelberg, and with my graduate student Simon Weisenborn, we showed that indeed there can be hyperons in the neutron star interior, but the 2 solar mass constraints actually pose a very strong constraint on the vector repulsion between these hyperons, among these hyperons. So this work was followed up by other contributors, and they proposed other mechanisms of increasing the vector repulsion with hyperons. And so these were summarized in a recent review that I presented with Isak Vidania. What is interesting is that these equations of state are from neutron stars. These provide us complementary information to those of terrestrial experiments. And the reason is this: if we look at the QCD phase diagram, well, this is a QCD meeting. I think all of you know this figure very well. So basically, compact stars lie at the low temperature, high density part of this diagram. And on the other hand, we have complementary information from terrestrial experiments. Like nuclear experiments, they probe densities around saturation density, and heavy ion collisions, on the other hand, probe intermediate temperature and finite and zero asymmetry, which means that the number of neutron protons are equal. On the other hand, compact stars lie at high densities and also at finite asymmetries, which mean they have, this is because neutron stars have way many more neutrons than they have protons. So the theories that can describe neutron stars will have to be extrapolated on 2 grounds. So one is, of course, to high densities, which is unknown from terrestrial experiments, and the second is asymmetry, neutron-proton asymmetry. So the other information that we get from heavy ion collisions and from hypernuclear experiments are potential depths of hyperons, and this I will come to later during my talk. So this uncertainty in the density and asymmetry gives rise to a large number of models, and phenomenological models particularly have been very successful in being able to describe properties of bulk nuclear matter and properties of nuclei. So it has parameters which can be adjusted to reproduce these nuclear and hypernuclear observables from terrestrial experiments. Now, let me describe to you what the problem is here. So basically, when we are extrapolating on with asymmetry and with density, like here we have the energy per particle and divided into the isoscalar and isovector channels, which means the first part is irrespective of neutron-proton asymmetry, and the second part takes into account this asymmetry. And you can see that there are various parameters, and these empirical parameters actually can be measured or can be derived from nuclear experiments. And for example, the saturation energy, the energy per particle at saturation is quite well known from nuclear experiments. The compressibility is fairly well known as well. But as you go to higher and higher terms, then the uncertainties become more and more large. And the same goes for the asymmetry. So this gives rise to a proliferation of models which have couplings which are fitted to different observables, and you can see that if we summarize them on a symmetry energy and symmetry energy slope plane, then they actually have different predictions and different correlations. And the question now arises whether these correlations are actually physical or whether they are spurious in nature. So a recent observation that can, a new field that can actually help us answer this question are gravitational waves. So this earlier today, Jocelyn already talked about the recent gravitational wave event 170817, which not only confirmed the gravitational waves from direct observation from binary neutron stars merging to form a hypermassive neutron star, but also it gave us a lot of information about the equation of state. And this was because the merging neutron stars are, because of their strong gravitational attraction, tidally deform each other. And this tidal deformation again depends on the compactness or radius, and therefore it helps us put constraints on the equation of state. I am particularly interested in what are called quasi-normal modes in neutron stars. And so gravitational waves are not only emitted by neutron stars in binary, but also isolated neutron stars can be very important gravitational wave sources. So if there are any kind of time varying quadrupole deformation in the neutron star, for example, if there is a bump or a mountain, as it is called, strong magnetic fields which deform it from its spherical symmetry, or other kind of fluid perturbations, then these can, when unstable, these can emit gravitational waves profusely. And so there are different modes like the F modes, P modes, G modes, etc. And they are classified according to the restoring forces that bring them back to equilibrium. And the axial W modes are actually pure space-time modes. So what is even more interesting is that not only in isolated neutron stars, these fluid perturbations can even be excited in the post-merger binary neutron star merger. And so this information might actually be embedded in the post-merger signal that we have not been able to isolate. So let's quickly review what information we have, what studies have been performed until now on the F mode instability in neutron stars. So these are basically fundamental pressure modes. And so the work regarding F mode started back in 1990s when Niels Anderson and Kostas Kokatas postulated that the F mode frequencies actually have a correlation with the average density of the star. So this is something which is expected. And they suggested also that if there are simultaneous observations of frequency and damping time from F modes and W modes, then one can very nicely deduce the mass and radius from these correlations. So this work was done with polytropic equations of state. Next, they they extended the same study for realistic equations of state. So here on the right, you can see the summary of the models that they used to perform this study. And you can already see from the mass radius curve, many of these have already been invalidated now with the two solar mass neutron star observation. So with these realistic equations of state, they again plotted the F mode frequency versus the square root of the average density. And they found a fit relation for the correlation. And so this is what they propose now as a more realistic fit. And this is called the astroseismology because basically they were trying to propose equation of state independent fit, and once the frequency and damping time or global variables like mass and radius are measured, then one can derive these from, if the frequency and the damping time are measured, then one can derive the mass and radius from such relations. But again, you see that the choice of equations of state is not exhaustive. And this was shown later again in 2005 by the group in University of Rome. And they took into account other equations of state, some even with hyperons, microscopic equations of state, and so on. And they showed, they proposed a different or a modification of the fit relation, as you can see from the figure. So now rotation was included by the group of Cockatus later, and they also obtained non-linear limit, a non-rotating limit of their calculations. And again, as you can see from the bottom figure, they showed that this plot relation from Anderson-Cockatus as well as this is different from what they are proposing now, and they have a different set of equations of state. So I think you get the point now. So the point is that we are trying to propose an equation of state independent relation by taking into account a choice of particular equations of state, which give you a fit, but if you change the choice of equations of state, the fit relation changes. So again, this study was done with polytropic equations of state, and later Daniela Doneva, she included realistic equations of state. So 5 of them, as you can see here, some don't satisfy the 2 solar mass limit. And not only the L equal to 2 modes, so L is the spherical harmonic index. She also studied the higher order modes. She proposed fit relations for higher order modes, L equal to 3, L equal to 4 modes. And again, if you can see the dashed lines in this figure, the fit proposed is different from those of the polytropic Costas-Cockatus paper and that of Anderson and Cockatus. The reason they considered higher order modes was this, that actually to determine whether F modes will be unstable to the CFS mechanism or the Chandrasekhar-Friedman-Schulz mechanism, one has to calculate the instability window. And they showed that for the lowest mode, the L equal to M equal to 2 mode, this would be negligible. In fact, it is only for the M equal to 3 and 4 modes that one can have a finite instability window. And this case is more optimistic when you consider realistic equations of state. On the other hand, they also showed that it's rather the L equal to 2 mode which becomes dominant for the post-merger scenario. So finally, I want to mention there is a recent paper also from the group of Bao and Lee, and they took into account a large number of parametrized equations of state, thousands of them, and proposed another scaled relation of the frequency with the mass and that of the compactness, and showed that these parameterized equations actually, this fit is equation of state independent. So with this review of literature, I wanted to probe these empirical relations in astroseismology and F modes, but this time with a systematic approach. So what I did was we took into account as the framework the relativistic mean field model, in which the baryon-baryon interaction is mediated by the scalar sigma, vector omega, and isovector rho mesons. The scalar meson has a self-interaction term. We also included the isovector rho omega interaction. And for calibration of the model, what is done is these coupling constants, like the G sigma, G omega, and so on. So there are 4 couplings which are isoscalar, and these can be determined from the nuclear saturation properties. And what we did was we took the state-of-the-art nuclear experimental uncertainties and varied the couplings within that limit. We also, so the other 2 couplings, which are actually isovector couplings, so these are fitted to the symmetry energy and the slope of the symmetry energy. And we also varied this within the current knowledge of uncertainty. So with this equation of state, so using the Lagrangian, we calculated the equation of state. and then we solved the perturbation equations, the fluid perturbation equations within the Cowling approximation, which means that we neglected the background metric perturbations. It is not a perfect scheme, but it is shown that it can affect F modes up to 30% at worst, and actually the scenario gets better for higher order modes. So these pulsation modes are solved with, so subject to boundary conditions at the center of the star and at the surface. So first we verified our calculations for well-known results from GM1 equation of state, for example, and then we performed the systematic study by varying one by one the saturation properties of nuclear matter, and try to see what effect this would bring on the F modes. So I show you here the uncertainty band in the pressure energy density relationship due to this uncertainty in the nuclear saturation properties, and the corresponding mass radius plot. So the equations of state are compatible with the latest observation of masses. Very surprisingly, we found that so the saturation and so energy per particle at saturation, the compressibility, the symmetry energy and its slope almost have negligible variations on the F mode versus mass, whereas there was a non-negligible but small effect coming from the saturation density. But actually the major uncertainty in the frequency mass relation comes from the effective nucleon mass, or the in medium nucleon mass. So we wanted to probe what, how this would affect the other observables related with F modes. And so first we determined the dimensionless tidal deformability as a function of mass for this range of uncertainty in effective nucleon masses. And they compare very well with the current observations of tidal deformability derived by the LIGO-Virgo collaboration and other recent works. And then we probed the relation between the F mode frequency and tidal deformability for this uncertainty regime of effective nucleon mass. And comparing this with the recent work of Bawanli, where they considered a lambda between a minimum and maximum value given by nuclear constraints and the GW170817. So we found these results to be compatible within our uncertainty band. The other interesting correlation that we can study is that of frequency with compactness, because compactness is something that is well determined from, it could be from gravitational redshift, it could be from the NICER data, for example. And we also obtained the variation. There is not much available in the literature regarding this, but we found a recent paper from Blasquez Salcedo, where they considered multiple modes. Now we also wanted to study now these empirical fit relations for astroseismology for our the uncertainty band of the effective nucleon mass and for the L equal to 2, 3, and F modes. So we obtained the fit relations, which now consider this entire span of uncertainty. And very interestingly, we found indeed the scaled frequency of the F modes are independent, equation of state independent, when we plot the correlation with the compactness. So now, with this interesting result, we went on to include the HYPERONs in this study. And the reason is this, that earlier I had performed studies including HYPERONs on other fluid mode oscillations, and I found a significant effect coming from the HYPERON presence in the core. For example, I studied in detail the HYPERON bulk viscosity, and they, it is well known now that our modes are very much affected by these. I had also probed HYPERONs and their effect on axial W modes, and also one can use axial mode frequency and damping timescale observations to differentiate between equations of state with and without hyperons. So in the literature, there is not much, many calculations about F modes with hyperons, but in this paper from Blasquez-Salcedo, they had considered our equation of state, Weissenborn, Chatterjee, Schaffner, and showed that this fit relation, the astroseismology fit relation, would be affected by the presence of hyperons. So the scheme is well known. So in relativistic mean field models, one can include the effect of hyperons by including hyperons in the baryons, the lowest baryons from the baryon octet in among the baryons, and so the nucleon-hyperon couplings, nucleon-hyperon interaction is mediated again by scalar sigma vector omega isovector rho meson, while the hyperon-hyperon interaction among each other is mediated by the strange scalar meson sigma star and the strange vector meson phi. So this time we took, again, the variations of the coupling constants for the nucleonic part with fixing the saturation density, energy per particle at saturation, and compressibility, while keeping only the variation of effective nucleon mass, as we had already determined this to be playing the major role in the F mode relations. And so for the couplings of the hyperons, they are determined in this way. So usually the vector meson hyperon couplings are fitted to the SU6 properties from the quark model, while the scalar meson hyperon coupling is fitted to the hyperon potentials in nuclear matter. On the other hand, one can do the same thing for the strange scalar meson sigma star on fitting it to the hyperon potential in hyperon matter. So this requires, again, some feedback from terrestrial experiments, and we already know that nucleon-nucleon interaction is fairly well known, while the hyperon-nucleon interaction is actually poorly constrained. So the hyperon-nucleon interaction, which determines the hyperon meson couplings, are also poorly constrained. Whereas for the case of hyperon-hyperon interaction, these are extremely scarce. So there is almost no data. The good news is that this situation will be improved by a large number of upcoming hypernuclear experiments at JPark, CERN, Brookhaven National Lab, and so on. So we have to keep a lookout for the developments. So now we included the effect. So now that we included hyperons in this calculation, we first wanted to verify the results with our earlier paper from Weissenborn et al. And so for this, we first switched off the isovector interaction, and the potential depth of the lambda particles. So there are, we considered the baryons from the baryon octet, the lowest baryon octet, which means there are the lambda hyperons, the sigma hyperons, and the cascade hyperons. So of these, the lambda appears first, and the potential of the lambda particle is well known. It is around -30 MeV. The uncertainty lies in the potential depths of the sigma and the cascade. And it is also suggested from experiments, hypernuclear experiments, that the sigma potential is repulsive. So this means that, so we actually performed this study in detail also in the Weissenborn paper. And we systematically showed that the variation of sigma potential to repulsive, so no matter what value of repulsive potential depth you put, the sigma will be eliminated from the core of the neutron star, and this would not affect the mass radius relation. On the other hand, the cascade potential, there is substantial uncertainty in the experimental data, And on the other hand, this also affects the mass radius relation. So what we proposed to do in this study was vary the effective nucleon mass within the uncertainty range and also the cascade potential to see how these affect the F mode relations that we want to study. The other thing that we already knew from our previous study in this Weizenborn paper, this paper actually did a systematic study of all the uncertainties related to the appearance of hyperons in neutron stars. And we showed that actually here, if you for example, if you see this equation of state plot on the left, you see that appearance of hyperons for sure leads to softening of the equation of state. But so the blue line here is the nucleonic case, and the other three are with including hyperons. So the one in which you consider both sigma star and phi mesons, and the one which in which you consider none of the two actually are not very different. On the other hand, if you include only the vector repulsion, which means you have the phi meson, so this vector meson repulsion actually makes the star more massive. And you can see that this is the only case which satisfies the 2 solar mass limit. This was called the sigma omega rho phi model in our paper. And so for this study, also we include only the phi meson for the interactions. So now let's go to see how the uncertainties in the effective nucleon mass and the cascade potential affect the F modes. So first we want to see both the variation, but first for a particular value of cascade potential -18, we varied the effective nucleon mass within the uncertainties. The bold lines in the mass radius curve, they are for the nucleonic case. The dashed lines are for the hyperons. And so we found that only for effective nucleon mass above, so below 0.6, the neutron stars were satisfying the 2 solar mass limit. So for these cases, we calculated the F mode versus mass. And you can see that these dashed lines, which are for the hyperons, in comparison with the bold lines, which are for nucleons only, we see a substantial difference between the corresponding masses. So this is with the hope that we can actually, when we have determination of frequency along with the measurement of the mass, we will be able to distinguish between the two cases. Now, if we, on top of this, we add the variation of the cascade potential within its uncertainty limit, we find that although this gives rise to a non-negligible effect on the mass radius as well as on the frequency mass plot, but again, in comparison, it is actually the effective nucleon mass which plays a major dominant role in determining the frequency as a function of the mass. We also calculated the same for higher order modes, and essentially we see the same behavior qualitatively, but there is a shift in the frequencies. So this is the preliminary result. On the left figure, we plot the frequencies as a function of the average of the density, and again, the variation of the cascade potentials play a less dominant role than that of effective nucleon masses. But what is more interesting is that this scale relationship of the frequency with the compactness remains universal. So I think I am at the end of my talk. So let me recap my results. So in the first part of the talk, I highlighted our work, which investigated basically the role of the underlying dense matter physics on F modes. So what we did was, within the framework of the relativistic mean field model, performed a systematic investigation of the uncertainties, the current uncertainties in the empirical saturation parameters, which are consistent with recent nuclear experimental data and with relation to F-mode frequencies. All the considered equations of state were compatible with the 2 solar mass observed maximum mass limit. We found the nucleon in medium mass to be the most dominant parameter, which affects the F modes as a function of mass and also the astroseismology relation. The saturation density had a small non-negligible effect. We also investigated this uncertainty in effective nucleon mass and its influence on the relation between F-mode frequency and tidal deformability, compactness, and the astroseismology empirical relations. We also extended this to higher order modes. For the second part of my talk, we extended this calculation to include hyperons in the neutron star core. And once again, we found the nucleon in medium mass to be playing the most dominant role in controlling the F-mode frequencies. So we also considered only the strange vector meson so that we can reproduce the 2 solar mass limit. We kept the lambda and sigma hyperon potential depths fixed while we varied the cascade potential within its current uncertainty range. We also determined the F-mode frequency for higher order modes. And so overall, it is the nucleon effective mass which played a more dominant effect than the hyperon potential depths on F-mode frequencies. And again, we probed the how one can have equation of state independent empirical relation with or without hyperons for gravitational wave astroseismology. So finally, in future, we have a lot of interesting things coming up. So first of all, there are these hypernuclear experiments which are going to improve our knowledge about hyperon-hyperon interactions, particularly the repulsive interaction. We also want to, we must include rotation and strong magnetic field effects if we want to extract F-mode information from post-merger remnants. One should also keep in mind that there are other exotic components of matter like kaons or deconfined quark matter that can affect the F-modes. Also, we look forward to the Einstein telescope, and it's predicted that the M equal to L equal to 2 and 4 modes should be detectable by the Einstein telescopes for sources in the Virgo cluster, or for the L equal to M equal to 3 modes by the advanced LIGO Virgo telescopes. And finally, I'm associated with the LIGO India project, which is an upcoming project of LIGO to be constructed soon in India. And this will definitely complement the other gravitational wave 3rd generation detectors. And so we are hopefully looking towards the future so that we can constrain the internal composition using information from F modes and other quasi-normal mode oscillations in neutron stars. So thank you very much for your attention, and please don't hesitate to ask me questions.
Thank you, Debarati, for this wonderful talk. So we have a few questions from the viewers. So the first question is, just a moment, from Bharat Kumar. Have you considered finite nuclear properties to fit the parameter set of the model? So what is the chi-square value when you fitted the parameter set?
Just a second, I'm trying to find the... Have you considered finite nuclear properties? Is this? Okay. To fit the parameter set of the model, what is the chi-square value? So no, for this model, so for this scheme, we did not consider the finite nuclear properties, but we did a similar study earlier. Maybe I can show you in one of my other slides. So we actually performed using, just a second. can you see my plots?
Yes.
Okay. So recently, so along with Jerome Margaron, we had looked at systematic study of a large number of models within and varying them all within their parameter space. So this was called a meta model, and the idea was that this is an effective density functional model. So we were trying to reproduce homogeneous and non-homogeneous matter in the crust and core within the same formalism. And for this, we actually performed studies, as you can see from this figure, for nuclear properties as well. But here, one can do that. I mean, because relativistic mean field models have, they have been applied, several of them, to determine nuclei, to study nuclei. But the problem is that for nuclei, there are other effects. So there are surface effects and so on. And so, I mean, one should also check the compatibility of these with nuclei. But for this particular study, I think we varied all of them, all the parameters within the bulk nuclear properties. So the uncertainty coming from bulk nuclear properties.
Okay. So he has another question. I'll just add it to it. So recently, many RMF equation of states have been developed and satisfied almost all the observational and experimental constraints, such as equation of states, B-GAPL, effusive Garnet, IOPB, etc. In your case, GM1 and GM3 are not satisfying low density data of PNM as well as neutron star radius. Could you please comment why you have chosen these USs and fitted further new US by varying effective mass?
Okay, so maybe I go back to the slide. Where, so I did not take okay, maybe I just show this part. So here the GM1 and GM3 were only reference models because they are relativistic mean field models. They are one point on the entire parameter space. So they were only used to compare the F mode calculations, which are available for some papers in the literature. But so the idea here, so we did not consider only the GM1 equation of state. I mean, this was only used to calibrate the F mode calculations. So for this work, what we did was we varied all the nuclear saturation properties within their entire uncertainty range. And yes, like you mentioned there, I mean, relativistic mean field models have been very successful in explaining, I mean, in reproducing saturation properties, like I said before, but I think you missed the motivation of this talk, which is that every time you choose certain equations of state, you satisfy some properties and you don't satisfy certain other. And they vary if you actually calculate the correlations. Not only this, but there are other correlations among the nuclear empirical parameters, and they are different for these models. And which is the reason also why, because every time you were calculating the astroseismology relation, depending on which model you choose here, the relation changes because they actually have different high density and high asymmetry behavior. So this was the motivation for this work.
Thank you, Debarati, for explaining. So there is one question I'll take from YouTube. Is the spectroscopic measurement of the star also seen?
I'm not sure I understand the question, but if you're talking about neutron stars in general, so yes. So for example, X-ray spectra, they provide information about the gravitational redshift and the compactness. I don't know, does that answer your question? I'm not sure I understood.
Yeah. So next one is about hyperons. You mentioned the hyperon puzzle and give a stiff equation of state, including the hyperons. How do you generate repulsive force between hyperons? I think this you have told already. Anyway.
Yes. So the hyperon, so the thing is, the hyperon-hyperon interaction is really not well understood, which is why we could vary the coupling constants, which were basically for the relativistic mean field model. They are the strain scalar meson sigma star and strain vector meson phi. When you determine them, you need to fit them to certain SU6, so certain quark model properties, or to the scarce hypernuclear potential depths. So the problem is that the experimental results are so scarce that they give us hints of whether they are just repulsive or attractive, but there is a large uncertainty in these potential depths, and therefore also in the couplings. So so like in this 2012 paper, what we did was we systematically studied how these uncertainties could actually lead to, I mean, probably we are missing some of these interactions when we calculate the maximum mass of neutron stars. So inversely, the maximum mass of neutron stars gives us information about the repulsive interaction of neutron stars.
Thanks. So there is another question about this hyperons. This is from Rana Nandi. You showed that the nucleon effective mass affects the F mode frequency the most, not the hyperons. Then it is not possible to say if there are hyperons inside the core from F mode observation. Is it right?
Sorry. Okay, maybe I will just go to this slide. So, hi, Rana. So, like for example, this figure on the right. So if or this figure on the right, for example, so you can see that it's not basically the hyperon potentials which tell you the difference between this, but okay, maybe this figure is better. So here you can see that the bold lines are from nucleonic case and the dashed lines are from the hyperonic case, right? So the difference in the so the uncertainty in the potential depth does not matter much, but of course you can see the presence of hyperon, what it does is definitely softens the equation of state and changes the relation between the frequency and the mass. So we would need additional information in order to understand whether there are hyperons. So it's not just the F mode frequency, but then we also need to study the damping times, etc., and whether maybe multiple observations of F modes can help us determine whether hyperons are there in the star. But this is like work in progress.
Okay. So next we have one basic question. The metric you considered is static and spherically symmetric. That is from Pratik.
Yes.
Yeah.
At least for this star, because we did not consider rotation and strong magnetic fields. Once you introduce these kind of things, like which introduce asymmetry in the system, then you will have to consider an axisymmetric metric.
Yeah. This question is from Shantanu. Do you also see F modes in white dwarf and other kind of stars?
Yes, F mode is a fluid perturbation. So these have been seen also in here in our institute. We have someone working on the same problem for heliosismology. So F modes are, I mean, also you see it for any kind of fluid perturbation. So these are very basic fluid perturbation equations. The only perturbation which does not exist in other stars is the axial W mode, because these are pure space-time modes, and only for neutron stars, which are extremely relativistic, these kind appear. But the F mode, P mode, G mode, all these modes are there in other stars, including the sun.
So at this point, I will add one question. Why you are only interested in F modes? I mean, why not the other modes?
Well, the F modes are among the first to be, because these are the lowest order modes, lowest frequency modes. So these are among the first to be excited. And also the calculations of Costas and his group showed that the instability window for F modes is actually quite so non-negligible. So this, I mean, we are trying to detect the other modes will also be excited, but at other frequencies, higher frequencies, and also for some, the conditions for them to be unstable is much more complicated. So these are, I mean, the most optimistic case when you consider oscillations to be excited in neutron star. And also it has already been shown that these F modes are related to, are actually related to the tidal deformability. So we might be able to find much more information with respect to F modes.
Okay. So the next question is again with F modes and rotation. This is from Jaikumar. Since the neutron star has to be very first spinning to produce large deformation, so is there a cutoff in the period of pulsar in order to produce F modes?
Cut off. Well, I haven't yet computed rotational F modes. These have been done in the works of Costas and his crew. So you can see here in this figure that there is actually a splitting of the F mode frequencies when you have rotation. So the whole picture is much more complicated. And as you said, yeah, these will be highly deformed. I'm not sure why there will be a cutoff, but I mean, yeah, I don't know. Yeah, I mean, for example, in the post-merger remnant, you have differentially rotating neutron star. So, yeah, these are much more complicated systems. I haven't yet performed this, so I will not be able to give you a better idea.
Okay. So the next question is from Prashanth. What is the source of your chosen variation in effective masses within RMF models? Have you looked at the variation in other many-body approaches, and if so, how does it compare?
You mean other many-body approaches in the sense like microscopic models?
Yes, I think so.
I think so, yeah. So, well, microscopic models are much more complicated because already they have a problem to in reproducing saturation properties. They have a problem to reproduce the 2 solar mass limit. For example, okay, maybe I'm going more towards hyperons, but the thing is that they need to also include 3 body forces in order to be able to explain the 2 solar mass, for example, which makes things much more complicated, and it's totally and yet unknown regime of the calculations. For the case of relativistic mean field models, this, yeah, I mean, the effective nucleon mass uncertainty is actually related to the uncertainty in the sigma potential. The sigma, so basically effective nucleon mass is the vacuum nucleon mass, and from that you subtract the sigma potential in the medium. And so there is an uncertainty in even the sigma mass, right? So I mean, yet there are still a lot of uncertainties related with effective nucleon mass and its density dependence. I don't think there is yet a very good consensus about the values of the effective nucleon mass, but these are like the current uncertainty range.
Okay. So the next question is from BC Paul. He asks, theoretically, neutron star upper mass limit is 2 solar mass. So why your study is confined with 2 solar mass, I mean more than 2 solar mass only? Is it due to observational limit we have now?
Why are the neutron stars above the 2 solar mass limit? No, I mean, you mean why not exactly 2 solar mass? I don't know what the question is, but well, the idea is that the theoretically predicted maximum neutron star mass should at least be able to explain the maximum observed neutron star mass. So this is what was observed. Is that your question?
Yeah. So we only consider those equation of states that can reach that 2 solar mass, at least 2 solar mass. So that's why we take those models only. I think this is his query. Next one, this is from YouTube. Why only consider F mode? Does it mean that only F mode is important? Okay, I have asked this question already.
Yes.
There is no more questions from the audience. If not, then we thank Debarati for this nice talk.
Thank you very much.